Hello, I am very glad to introduce our work in the Interspeech 2020 virtual conference. The title of our paper is Speaking Speed Control of End-to-End Speech Synthesis Using Sentence-Level Conditioning. This is Jae-Sung and these are my co-authors, and we are all from Speech AI Lab and NCSoft. Thanks to the advance of NeuroTTS system, we are now actually using synthesized speech in many areas. For example, in video dubbing and expressive style speech synthesis. To extend the usage of TTS system in real-world scenario, speaking speed control is essential. For example,
필드 사냥으로 캐릭터를 성장시킬 수 있습니다. 필드 사냥 시 천하무림 퀘스트를 활용하면 에픽 퀘스트보다 빠른 캐릭터 성장이 가능합니다.
This is the tutorial video of our game, and speech used in this video is generated by TTS system. Currently, we are modifying the length of video or the text content according to the length of speech. However, with speaking speed control, we can generate speech according to the desired length of video. Also, because the speaking speed should vary depending on the context or the situation, speaking speed control is also important in expressive style speech synthesis to generate more natural speech that fits in the speaking situation. There are two kinds of previous approaches for speaking speed control with neural TTS system. The first approach is with unsupervised prosody modeling. These approaches define various speech attributes in an unsupervised manner because the speech attributes are very difficult to be defined objectively. This method extracts the speech attributes from a reference speech and then generates similar styles of synthesized speech to the reference speech. Global style token-based style encoder is one of the famous model, and this model in training stage learns GSTs to contain the speech styles that appear dominant in the training dataset in an unsupervised manner. And then in the inference stage, this model can control the speech style using the weight of GSTs. However, these approaches require a large amount of training dataset in variety of styles because they're learning by unsupervised manner. And secondly, they cannot guarantee what speech attributes will be modeled, which means that we cannot guarantee that the speaking speed will be always represented in GSTs. And finally, they cannot perfectly disentangle each speech attribute. For example, pitch and speaking speed can be entangled and represented in the same GST. The second approach is by phoneme level duration control approaches. For example, there are phoneme duration control TTS model and fast speech model. These approaches control the speaking speed by modifying the phoneme level speech duration. So they need the additional phoneme duration information during training. The cons of these approaches are that they require extra well-trained ASR or TTS model to extract ground truth phoneme duration because it is needed in the training stage. And to train this pre-trained model, the large amount of extra data and domain knowledge are needed. And they are difficult to control the speaking speed naturally. This is because the people control their speaking speed by varying their speed differently according to the consonant, vowels, or words. However, these approaches increase or decrease the duration of each phoneme at the same rate for an entire sentence, so the naturalness is not very good. So to overcome this constraint, we propose a simple and effective speed controllable TTS system, which is SCTTS. It controls the speaking speed with sentence level speaking rate value as an additional input. And we improve the robustness of speaking speed control by adapting the GST to the SCTTS system. The key strengths are as follows. First, it does not require any well-trained additional models to extract ground truth phoneme duration because this system only uses the sentence level condition. And secondly, it is trained in an end-to-end manner and have a simple training pipeline. And then it can also control speaking speed of speech more naturally than the other phoneme level duration control approaches. And with GST, it can control the speaking speed while retaining other speech attributes such as pitch. So this is the architecture of the SCTTS system. As you can see, the sentence level speaking rate value is given as an additional input to text encoder. In training stage, inverse mean duration is used as a SR value measurement like this. The R here is the SR value, and lambda here is a SR scaling factor, and P here is a number of phoneme sequences. And finally, the T is the length of MEL spectrogram. And in the inference stage, the desired SR value are given and generated the MEL spectrogram with corresponding the speaking speed. As you can see, the SCTTS does not require any pre-trained models and can be trained in end-to-end manner because the SR value can be simply calculated during training stage. In our experiment, however, we found an issue about entanglement of speaking speed and other speech attributes, especially when this SCTTS system were trained with the expressive speech dataset. This is because in expressive speech, the multiple speech attributes such as F0 can be correlated with speaking speed. For example, this graph shows the average F0 value according to the speaking rate value of our two kinds of dataset. First, in our neutral style dataset, the F0 almost remains and almost unchanged as the speaking speed changes. However, with our highly expressive dataset, the F0 value changes in a wide range as the speaking rate value changes. More details of our dataset will be described in the experiment section. Therefore, when the SCTTS system were trained with expressive speaker dataset, the SR value not only controls the speaking speed but also other speech attributes such as F0 in here. So to overcome this, we adopt the GST-based style encoder to disentangle and control the speaking speed from other speech attributes. We named the GST adapted SCTTS system as SCTTS-GST. This system disentangles the speaking speed from other speech attributes by incorporating the GST-based style encoder. The GST-based style encoder is expected to learn style features other than the speaking speed. This is because the GST encoder are learned in an unsupervised manner and because the speaking speed is given as an additional input as a speaking rate value, so the GST encoder will learn other features than the speaking speed. So with this model, the SR value can only control the speaking speed. Yeah. For the experiment, we use the two kinds of dataset, which are neutral dataset and the expressive dataset. The models were trained with each dataset separately, and the speaker of each dataset were Korean female and Korean male. The speaking style was neutral and narrative style, and with expressive dataset, it contained various expressions such as neutral, excited, shouting, shying, etc. The amount of dataset was 8.7 hour and 11 hour. For the baseline TTS model, we used the modified deconvolutional TTS model, and the SR scaling factor was 100. We used the Adam optimizer and the WaveGlow trained with 50-hour speech as a neural vocoder. So the result of SCTTS, we used the average SR value to obtain the SR value obtained from the training dataset to generate a normal speed speech, and then increase or decrease the SR value to generate fast or slow speed speech. So the results are like this, and as you can see with neutral speaker dataset, the speaking speed can be successfully controlled without any changes in other speech attributes. However, with expressive speaker dataset, as the speaking speed becomes slow, the FGR values are also increased together. So, which means they are entangled. So, with GST modules, this model is trained with only expressive speaker dataset, and we use two different kind of reference speech to obtain the style embedding from the GS2 layer in the inference stage, which is first one was normal style speech represented as N and have average F0 value. The second is excited style speech represented as H and has high F0 value. As you can see in this both mouse spectrogram, as the speaking speed changes, the FGR values are almost unchanged. And the right graph represented the average FGR value of the synthesized speech and according to input speaking rate value. As you can see, without GST module, the SCTTS model, the average FGR changes in a wide range as the speaking rate value changes. However, with GST module, the average FGR value is almost unchanged with the normal reference speech. Normal reference speech, and with high reference speech, the changes were much less. So we can disentangle the speaking speed from FGR value with GST module. For the naturalness evaluation, we conduct the MOS listening test. We compare our model with phoneme level duration control TTS system, which are PDC-TTS and fast speech. All models were trained with expressive speaker data. Our system outperforms other systems, especially in slow speed speech. We suggest the two reasons for this. The first reason is that other systems generate slow speed speech by lengthening every phoneme, word, or silence with the same rate. However, our system do not. And secondly, the unnaturalness of speech was more noticeable with slow speed speech, so this can be also one of the reasons. Now let's hear some demo samples. First, the SCTTS system trained with neutral female speaker. The normal speed speech first.
설날의 아이들은 어른에게 절을 합니다.
And then fast.
설날의 아이들은 어른에게 절을 합니다.
And then slow.
설날의 아이들은 어른에게 절을 합니다.
So as you can hear with neutral female speaker, the actual values are almost unchanged. However, with expressive male speaker, the normal first.
잡아당긴 타구는 왼쪽에 파울.
And then fast.
잡아당긴 타구는 왼쪽에 파울.
And then slow.
잡아당긴 타구는 왼쪽에 파울.
Yes. So as you can hear, as the speaking speed becomes slow, the FGR values are increased. So we adapt the GST module and with normal FGR reference speech, the normal speed first.
잡아당긴 타구는 왼쪽에 파울.
And then fast.
잡아당긴 타구는 왼쪽에 파울.
And then slow.
잡아당긴 타구는 왼쪽에 파울.
Yeah. So and with high FGR reference speech, the normal speed.
잡아당긴 타구는 왼쪽에 파울.
And the fast speed.
잡아당긴 타구는 왼쪽에 파울.
And the slow speed.
잡아당긴 타구는 왼쪽에 파울.
So with GST modules, the speaking speed can be controlled while retaining the FGR value. More samples can be here in this link. So for the conclusion, we propose a simple and effective speed controllable TTS system with sentence level speaking rate value as an additional input. It does not require any extra pre-trained models and can be trained in end-to-end manner. SCTTS can generate more natural speech with various speaking speeds, and with GST module, it can disentangle the speaking speed from other speech attributes such as pitch. And they outperform the conventional phoneme duration control TTS system, especially with slow speed speech. Thank you for listening.